In this video, we're going to talk about binomial probability, and by the end of the video, we're going to come up with a binomial probability formula. But first, I would like to start with some definitions that we need in order to basically come up with our formula. First, the definition of a Bernoulli trial, sometimes called binomial trial, and a Bernoulli trial is a random procedure with exactly two possible outcomes, which are going to be categorized as success or failure, in which the probability of success is the same every time the experiment is conducted. Some examples of Bernoulli trial: tossing a coin once. And we're gonna, we have two possible outcomes, either heads or tails. And depending on how we define our event, it's gonna be success or failure. If we bet on heads, then heads is success, tails is a failure. Now, depending on the coin, the probability of the success and failure is the same. So if the coin is fair, then the probability of heads is a half, and the probability of tails is a half. If the coin is unfair, then the probability of heads and tails are not going to be the same, but they're still going to be they're not going to be equal to each other, but they're going to remain the same no matter how many times we flip the coin. I hope you guys understand that, the difference. Okay, so then asking yes or no question. Again, there are only two possible outcomes, therefore it's a Bernoulli trial. Now, figuring out probabilities for those outcomes is a little bit more complex. So basically, we're gonna rely on frequency approximation method, basically judge the probability from the data that we already acquired before. Okay, and the next example is guessing an answer to a multiple choice question. Again, if we're guessing, meaning we don't have any information, but we're just purely selected any answer out of the four possible choices, then the outcomes are success if we guess it right, and failure if we don't guess it right. Now, what about the probability of success versus the probability of failure? They're not the same, right? Only 1 out of 4 questions is correct. That means the probability of success, or guessing that one correct answer, selecting that one correct answer randomly, is 1/4 or 0.25. Now, selecting a wrong answer is 3 out of 4 or 0.75. So I think, I hope this, guys, this is clear about Bernoulli trials. Well, let's go forward to binomial experiment. So binomial experiment or distribution of the variable results from repeating Bernoulli trials and number of times. So which we take Bernoulli trial and repeat it again and again and again. So this experiment satisfies the following. The procedure has a fixed number of trials, so not infinitely. We will have a fixed number of trials. Let's say 10 Bernoulli trials or 15 Bernoulli trials, so forth. That's number one. Number two, the trials must be independent, which means that the outcome of the previous one does not affect the probability of the outcome of the second trial, right? So when we're flipping a coin, we kind of like, in terms of probability, we're starting all over again. So whatever we got on the first trial is not gonna influence the probability of success on the second, and so forth. And so that's number two. And number three, each trial must have all outcomes classified into two categories: success and failure. And we already talked about it earlier when we discussed the Bernoulli trials. Okay, some examples of binomial distribution. And here we're invited to actually analyze and say whether we think it's a binomial distribution or not. So example number 1, randomly selecting 12 jurors and recording their nationalities. I'll give you a couple seconds to think about it. Pause here if you have to. What's your answer? So the correct answer would be no, because we have more than 2 possible outcomes, right? If we're have 12 jurors, their nationalities could be, there's more than 2. Now, let's look at the next one. It says randomly selecting 12 jurors and recording whether there is a no response when they're asked if they have ever been convicted of felony. Again, pause here if you have to think about it. The correct answer is yes, this is a binomial distribution. We have 12 jurors, so that's 12 trials. The outcome of each trial is yes or no. No, so no being a success and anything else being a failure, so 2 possible outcomes, and the probability of a no is the same from one trial to another. Okay, let's take a look at number 3. Treating 50 smokers with Nicorette and asking them how their mouth and throat feels. Again, pause here if you have to. The right answer is this is not a binomial distribution because there is a variety of answers to this question. It's not just 2 outcomes, right? So how can we rephrase this question so that it will result in a binomial distribution? Number 4, treating 50 smokers with Nicorette and recording whether there is a yes response when they're asked if they experience any mouth or throat soreness. So now the 2 possible outcomes are yes response as a success, and anything else would be a failure, right? No, or yeah, so that would be 2 categories for the outcomes. The number of trials, 50. We're asking 50 people. And then the probability of success stays the same from trial to trial. And number 5, recording the number of children in 250 families. So again, this is not a binomial distribution because the possibility of answers is endless, right? It's not just 2 possible answers. Okay, so let's take a look at this example, which will lead us into a formula for calculating binomial probabilities. So this says a test consists of multiple choice questions, each having 4 possible answers, A, B, C, or D, one of which is correct. Assume that you guess the answers to 6 such questions. So I want to stop. I want to stop here for a second and want to write down a couple of things. So first of all, success, what do we consider success? Success is guessing a correct answer, right? Guessing correctly. Okay, and what's the probability of success? Well, again, if you need to pause to answer this question, please do so. And we're going to continue. If we have 4 possible answers and only one of them is correct, that means that probability of success is 1 out of 4 or 0.25, and we already talked about it. what's the probability of failure? Well, first of all, if there is only two possible outcomes, that means they're complements of each other, right? So we could figure out probability of failure in two different ways. Literally just count the possible wrong answers, like 3 out of 4, and that will give us 0.75. Or we could just do a complement of a success. So that would be 1 minus 0.25, which will also give us the same 0.75. Okay, so with those clarified, let's continue. So question A says, use the multiplication rule to find the probability that the first two guesses are wrong and the last 4 guesses are correct. So that's going to be a sequence, right? We have a binomial distribution because we have a Bernoulli trial where the probability of success is 0.25 and probability of failure is 0.75. But then we repeat it. We repeat this guessing procedure. How many times? 6. So 6 questions. N equals 6. We repeat the procedure 6 times. So now we're looking for the probability of this sequence. So the first 2 questions are wrong. So failure, failure, and the rest are correct. So we have 4 correct answers. Okay, so using the multiplication rule, we're gonna use the probability of failure times the probability of failure times the probability of correct 4 times in a row. So what is that? Or success, failure, sorry, success, 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 success. Okay, so we already know that probability of failure for one guess is 0.75. So it's going to be 0.75 and 0.75. And the probability of success is 0.25. So it's going to be 0.25, 0.25, 4 times, right? So in the end, this is 0.75 raised to the second power multiplied. I'm running out of room here. Okay, so multiply by the probability of success, 0.25, 4 times. And when I put it into a calculator, I will get approximate. So that's my answer to the first question. Okay, so now, oh, they wanted us to use this notation, and we used failure, failure, success, 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 which is the same. You guys understand that, right? Okay, so beginning with this situation, 2 first failures and then followed by 4 successes, make a complete list of different possible arrangements of 2 wrong answers and 4 correct answers. Then find the probability of each entry in the list. Okay, let's list them all. So we have, so in other words, they're asking, in how many ways can we get 2 wrong answers and 4 correct answers? Is it only 2 first can be wrong, or the wrong answers could be anywhere? Like if the final result is 2 wrong and 4 correct, and how many ways can we get that result? So, well, we could have the first one failure, right? Wrong. And then 4 correct answers and the last one wrong. That's one possibility, right? And then we also could have the first one wrong and then correct, 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 wrong, correct. That's another possibility for 2 failures among 6 questions, right? And then we could have failure, success, success, failure, success, success, and then failure, success, failure, success, 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 and actually, and then we could have success, failure, failure, success, success, success. Okay, we're gonna stop here, stop listing. I mean, this list goes on, but let's figure out the probability here. So using our product rule again, we're gonna have the probability of failure times the probability of success times the probability of success 4 times, right? And multiplied by the probability of failure. So actually, now if we look at this, it's the same product because we change the factors, the product is the same. So we're still going to end up with 0.75 to power 2 multiplied by 0.025 to power 4, right? Which will result in the same 0. Now, so continue this reasoning. We're going to reason that all of these are going to have the same probability, right? So because we're still going to have 2 failures, so 2 factors of 0.75 and 4 successes, so 4 factors of 0.25. So they're all the same. 0.75 to power 2 times 0.25 to power 4. Now, in order to figure out, okay, so, and that's going to be our question C. Based on the preceding results, what is the probability of getting exactly 4 correct answers when 6 guesses are made? So basically, the addition rule says that if we just want to figure out the in general, the probability of 4 wrong answers and 4 correct answers and 2 wrong answers, then we need to figure out each of these probabilities and then add them up, right? Okay, because we're gonna get 2 wrong and 4 correct either this way or this way or this way or this way, and or results into addition rule. So if we want to figure out the total probability, what we need to do, we need to figure out how many ways can we configure 2 failures and 4 successes. Now, I want you to pause here and to think about, do we have a tool to answer how many ways can we combine 2 failures and 4 successes? And the answer is, yes, we do. We have our combination formula, right? Because it doesn't matter in which places our F's are, as long as there's 2 of them. And same goes for S's, successes. Okay, so we have our NCR formula. So N is 6. We have 6 selections to make, right? 6 guesses. And then C, and how many successes do we want? We want 4. So it's gonna, our formula is gonna look like this. It's gonna be 6 C4. And when we enter that into calculator, we're gonna get 15. So there is 15 different ways to have 2 failures and 4 successes. So the probability of each of them being 0.00. So basically what we need to do now is to multiply 0 by 15 to get the probability of 2 failures and 4 successes. So probability of 4 successes out of 6 total guesses is going to look like this. We're going to have 15 multiplied by 0.0022